Okay, continuing. So any system that is away from equilibrium will favor moving toward equilibrium. An equivalent statement would be that a system away from equilibrium will spontaneously move toward equilibrium. Spontaneous reaction does not mean it will move quickly toward equilibrium. This is very important because of the word spontaneous kind of means it just happens, right? And that's exactly what it means. It doesn't give us any kinetic information. It means that this process is favorable and it will move in this direction without any need for anything to happen or any input of energy. So it's important to separate kinetics from thermodynamics, as we will see later. Also note that equilibrium is the endpoint of a reaction or process. Very important. So when we're looking at the reaction y goes to x, an initial reading of this would be, well, the endpoint is when all reactants y are turned into x, but that is not true. The endpoint is when y goes to x reaches equilibrium. And at that state of equilibrium, you could have still reactant left over. So it depends on the equilibrium constant. So if our equilibrium constant from above, which for y goes to x was 10, that means at equilibrium, for every 10 product, I will have one reactant left over. If I try to make more of the reactant in the product, actually move away from equilibrium, and there needs to be an input of energy of some sort, or this reaction has to be coupled to a second reaction for this to happen. So equilibrium is the end state. This is the state of maximum entropy. In order to move a reaction away from equilibrium, the reaction needs to be coupled to a second reaction that will increase overall entropy. As we will see, there are two types of reaction or processes that exist in a cell. So we have active processes that move a system away from equilibrium. These processes decrease entropy and are coupled to reactions that are favorable so that overall entropy is increasing, such as coupling to ATP hydrolysis. Number two, passive processes that are systems that are away from equilibrium that are then allowed by a cellular mechanism to move toward equilibrium. The energy from a process or reaction moving towards equilibrium can be harvested to do work. So the first one is going to decrease entropy. The second one, the passive processes, will increase entropy. So as long as you couple a passive process to an active process, where the passive process is increasing entropy more than the active process is decreasing entropy, when you add them up, overall, you are increasing entropy. An example of this is aerobic cellular respiration. The breakdown of glucose or other molecules to CO2 and H2O lead ultimately creating a proton gradient across the inner membrane of the mitochondria. The protons are then allowed to move down their concentration gradient through a membrane protein called ATP synthase, which harvests that energy to produce ATP from ADP and inorganic phosphate. Therefore, the energy from foods we eat is used to power processes that move systems away from equilibrium in order for some of these systems to move towards equilibrium. The energy from processes moving towards equilibrium can be used to maintain life. So essentially what you're doing is the food that you eat, the energy that's harvested from that food, is moving some systems toward order. So decreasing entropy. And we have said that if you want to decrease entropy, that will be a process that has a delta G greater than 0. Then these processes that have been moved away from equilibrium, meaning maximum entropy, are allowed to bounce back toward equilibrium. Therefore, now delta G is less than 0. You're actually increasing entropy, but with it, what it'll do is it'll take a second process that we have here and move it away from equilibrium. Now, this explanation and what we're saying right here might not be super clear, And I'm not going to get into it at this moment. And the reason why is that we're going to be using this idea later in section 2. So the whole purpose of this whole section here is to introduce you guys to these ideas, delta G, entropy, and etc. And then we're going to use it later in section 2. So kinetics of a chemical reaction. Thermodynamics of a chemical reaction, delta G and K, do not give information on how quickly a reaction will reach equilibrium. Thermodynamics and kinetics are two different things. So if you have a reaction that's very favorable, like ATP hydrolysis, ATP hydrolysis has a delta G standard that is much less than 0. It's a very favorable reaction. But there's plenty of ATP in your cells and there's plenty of H2O, and this reaction doesn't simply happen by itself. So the reaction by itself, ATP hydrolysis, although it's very favorable, its kinetics, without the involvement of an enzyme, is very slow. So just because a reaction or a process is very favorable does not mean that it will happen very quickly. The two things are separate. The rate of a reaction is dependent on energy of activation, or activation energy, EA, of the reaction as shown below. So let's look at our favorable reaction, Y goes to X. And reaction progress diagram. And this reaction is favorable, so we'll put Y over here. And we'll put X down here. And we had a delta G standard that was less than 0. In this case, for our example, it was, I believe, negative 5.9 kilojoules per mole. But the progress of the reaction actually goes through a little bit of a bump here, and then it goes back down. So the difference between the top here and the reactant Y is called the energy of activation. This thing right here. So a reaction must go through this top part right here to go towards product. Y has to be transformed to something, which is in this top where the green arrow is pointing, to eventually become X. And for X to become Y, it also has to go through that top part where the arrow is pointing. So for the reverse reaction, if I was going to draw out the reverse reaction of X goes to Y, Y would be over here at the same level, and X would be down here. And my energy of activation for this reverse process would be this reactant, top of this little hill. This would be my energy of activation for the reverse process. And of course, the delta G would be this. Delta G standard. We're assuming, just to make sure that we're super clear on this, that we're under standard conditions. That's why we have delta G standard here. Anytime I put delta G standard, that means we have equivalent amounts of X and Y. So the top of the EA peak is called the transition state, and it is represented by molecule or molecules that are neither product or reactant, but something in between. Let's draw out our reaction progress diagram again for Y goes to X. We have Y, we have X, and we have our reaction. So this thing above right here is going to be the transition state. So I'm just going to write TS for transition state, okay? There is a molecule up here in the transition state. It's an in-between molecule. It's neither Y nor X. It's some in-between state. For those of you who have taken organic chemistry, you're a little bit more familiar with this. You know kind of what the transition state looks like for different types of reactions. But it's just an in-between state, right? A high energy state that is only around for a very short period of time. And here's my EA. So this would be the EA of the forward reaction. So forward. Now the EA of the reverse reaction would be this. So let me use a different color. This would be the EA of the reverse reaction. X goes to Y. just to make sure, this is y goes to x, and this is x goes to y. For a reaction which favors the forward direction, the EA of the forward reaction is less than the EA of the reverse reaction. And that is being shown here because we can clearly see that EA forward is less than EA reverse. Right? That's you can clearly see that in this picture. Again, we're under standard conditions here, so just to make sure. Okay, so under standard conditions. So what does an enzyme do? An enzyme will lower the EA of a reaction by stabilizing the transition state. So here you can see in this picture, we have our y goes to x. You can see, okay, here's my EA right here, and it's being shown right here. And you can see that the enzyme has come in and lowered the EA. Right, so this is EA normal, this is EA cat for catalyzed. So the enzyme will interact with the transition state molecule. It will stabilize the transition state, lowering that top of the hill down, and that will make the energy of activation barrier much less. By making the energy of activation barrier smaller, the rate by which the reaction moves will be faster. Note, lowering the EA of a reaction will increase the rate of the forward and reverse reaction by the same amount. Actually, let's take a closer look at this. So here's my reaction progress diagram for y goes to x. Again, we're under standard conditions. I just want to make sure we're aware of that. So concentration of y equals concentration of x. So here's our uncatalyzed reaction. And we have an EA for this uncatalyzed reaction. And the reverse reaction's EA will simply be this right here. EA reverse. And let me just put forward here for this. Okay. Now, if I put in an enzyme for this reaction, so we add the enzyme for this reaction, what will happen is the transition state will be brought lower. So here's our transition state right here, and this is going to come down. So now we have this, right? So this is our reaction pathway for the catalyzed reaction. So what is the new EA for the forward reaction? Well, the EA for the forward reaction is right here. EA cat forward. What about the reverse reaction? Well, the reverse reaction, let me go out here, here, here's the EA cat reverse. So you can see both of them have been lowered. And when we do a little bit of math to calculate this, you will see that both have to be lowered by the same amount. It is an absolute requirement. An enzyme will not specifically catalyze the forward reaction, but not the reverse reaction, and vice versa. At equilibrium, delta G equals to 0, the rate of the forward reaction, in our example y goes to x, equals Vf. The rate of the reverse reaction, which would be in our example x goes to y, will equal to Vr. So at equilibrium, where delta G equals 0, the rate of the forward reaction will equal to the rate of the reverse reaction. So let's take a look at this. So y goes to x, and now the concentration of x over y equals to k, the equilibrium constant. So here's our reaction progress diagram. So now we're not under standard conditions. X over y equals to the equilibrium constant. So now what will happen is the level of y will equal to the level of x. The reaction will still have to proceed through the transition state. So there's still an EA, but the EA of the forward reaction and the reverse reaction equal each other. There's no difference. And delta G equals to 0 because there's no difference between the levels of y and x. So before pushing forward, we can kind of go and look at what we did before. Because now we're talking about rates, and we're talking about the forward rate or the reverse rate being favored, and etc. So when we're looking at this picture right here, and let me actually move it a little bit this way, and come down. So we can see that, okay, let's get rid of this stuff. This is looking at y goes to x in this direction. And we calculated all these numbers, all these delta G's, based on the ratio of x to y, right? So here we can say that, okay, we have a very positive delta G. It starts to get closer to 0, and then you're at equilibrium, right? So if I'm looking at this and I want to just show what's happening with arrows, I can say that, well, in this case, y goes to x here for this one. It favors the reverse reaction more than the forward. So I can say that, okay, well, this actually is more like this instead of a single arrow, right? For this one right here, I can see that, okay, the forward reaction is still not favored, but not as much as before because we have 5.9, which is less than 11.8. So here I can say that, okay, this is still here, but now the forward reaction is picking up. At equilibrium, I can say that, well, y and x, y goes to x and x goes to y are happening at the same rate. At negative 5.9, now the forward reaction is favored, but not by a lot. So I can say that, okay, well, forward reaction is favored, but so is the reverse. The reverse is not as favored, but it's happening. It's not something that can be ignored. Here, now the forward reaction is even more favored over the reverse. So here I can just kind of go like that, and so on. So just to give you an idea of what's going on, these arrows that we draw, like for example here, this is just telling us, hey, we're looking at this reaction in this direction. It doesn't give us any other information, it's just telling us our point of view. And when you're looking at delta G's, you can actually put in arrows that are more meaningful, like we've done here. Okay, we'll stop here and continue the rest of the material later. Okay, thank you.